Hello, everybody. This is the week 5 and the second lecture we will conduct. And as you remember that on Tuesday in the first lecture, we just started to discuss about open channel flow, and I explained to you what is Froude number, and then also I explained you what is critical flow, and then you learned that how to decide if a flow is subcritical or supercritical. And if Froude number is larger than 1, it is going to be supercritical. If Froude number is less than 1, it's going to be subcritical. Also, you can use the critical depth as a kind of comparison. If the height of your flow is higher than, the critical depth, then it is a subcritical flow. And if the height of, the depth of flow is less than critical depth, then you are going to have supercritical flow. And also, I'd like to remind you that there are always two possibilities with the same specific energy. You are going to learn today. So the flow could be subcritical or supercritical. And it is always a question that what kind of flow you are going to have. And most probably you are going to ask that, ask to identify the type of flow and alternating depth for that type of specific energy. That's why today we will continue learning what is specific energy. And let's start the topic. And sorry guys, still I have problems in my throat. That coronavirus still has an impact on me. It is passing not fast. Okay, so the specific energy topic is important in open channel flow, guys. Listen me carefully. Try to understand everything. And if you do not understand, if you have a little hesitation in your mind about the topic, just ask me, please. Because it is important that you should learn and understand everything at this stage during my lecture. Otherwise, you might have some difficulties understanding. It's a bit complex topic because I think you have never seen such a thing before in energy calculations. That's why some of my students in earlier times, I've been teaching this course for more than 15 years. And my experience that students are going to have a little bit difficulties to understand and grasp what's going on here. So let's be careful and listen carefully, okay? It's an interesting topic. Okay, let's first write the energy equation like we did it in pipe flow. As you remember that in pipe flow, the energy equation turned into Bernoulli equation. So you may remember that if we like to express everything in hertz, like in meters, the total energy is equal to elevation. It is the potential energy plus hydrostatic energy, pressure over rho g, and the kinetic energy. It is velocity head actually, velocity square over 2g. So this is the equation and the energy. This is the total energy equation. It is the same for the open channel. Okay, there is no difference, but there is only one difference. You know that we don't have pressure in the system. Okay, for example, if you immerse here let's say submerse. Okay, actually, immerse is going out, submerse is going in. Just give me 1 second. Okay, let's assume that you are immersing here a pipe. Okay, like a kind of pipette tube. Okay, so I have a simple question. You know that in the pipette tube, so not pipette tube, a piezometer. The piezometer has always an open end, so it is open to air. So my simple question is that what should be the water height in that pipette tube? In this, sorry, not pipette, in this piezometer tube. What should be the water height?
It's open flow, right?
Yeah, it is open channel flow.
The water will not rise then?
Yeah, it is going to be exactly like this, isn't it? The same level with the water flow, right? So that's why we assume that the pressure in the open channel flow is equal to that height, okay? So P over 2 rho g is equal to what? Okay, the depth of water, that's all. It's simple. So yeah, let's take the Z value, like the altitude value or the elevation value of the channel is constant, because the slope is quite a kind of small number. Like we are making the design of open channel flow channels like one out of 10,000 or 1,000 range. I mean, the slope is around 0.001. So it is quite a small number. The difference is quite something like 1 meter in 1,000-meter length. So let's assume that Z is constant for any given point, like this one, any given point. If less is constant, we can take this Z value as a 0, and P over G, I mean, the pressure head is going to be equal with the depth of the water. So you are going to replace this value with Y, and then the energy equation turns into Y plus velocity square over 2G, okay? So this value, actually, this value is called specific energy. It's simple, isn't it? Any question, guys? Any question? No?
No.
Okay, this looks simple. Let's make it a little bit complex. Okay. And if you calculate velocity, the velocity is equal to flow rate over area. Area means depth times water, I mean channel width, and channel width is always B, guys. Okay, don't get confused. In open channel flow, if you see that if you see B values given, B is always channel width. Okay, B is always referring to channel width. For open channel flow, if it is rectangular, B means the surface length, okay, surface width. Okay, the surface width of the floor, because it's equal to the other, I mean the channel width. So the velocity can be calculated in that way. And if you replace the velocity value with velocity square or 2G part, and then you are going to get this value. Okay. And also you may remember from earlier section that you know that how to calculate the critical depth. The critical depth is equal to that equation is given on the screen. Just follow my cursor. I am going to do some annotation. Okay, this is the critical depth. And also there's one more thing I am going to introduce right now. It is the small q value. Okay, the small q value. It is okay. And in order to make the calculations easy, some hydraulic engineers prefer to remove the B value. I mean the width, channel width value, because width is constant in everywhere in that channel. So they don't like to deal with the B value, and they just invented a kind of easier notation of flow rate. And the flow rate is given as Q, is small q, it is a flow rate over B. So one trick, guys, if you read any question in hydraulics exams or in practical life, any hydraulic, I mean civil engineer problems, and if you see that if flow rate is given as cubic meter per meter square area, actually, I'm sorry, meters cubic meter, not cubic meter, meter square per second, okay, not cubic meter. Instead of cubic meter, if it is given like square meter, okay, then just remember that it is not capital Q, it is not the flow rate, it is the unit flow rate, okay, discharge per unit. It is unit flow rate. It's called discharge per unit weight. And even the exams, some of the students are just realizing that they just thinking that, oh, professor made a mistake and gave the flow rate as like square meter over second. I think this is a mistake, and they are taking as a kind of cubic meter. So this is important. I am not making mistake. In open channel flow, it is in most of the problems. If you look at the other books and other sources, you will see that the flow rate is given in that way, but it is not actually the flow rate. It is actually the flow rate per unit, okay? Per unit width. This is not width. Okay, so it is discharge per unit width is small q. And you can rewrite the critical depth by making a kind of proper replacement. Then you can get with this equation. Okay, this is another equation which is exactly used for calculation of y critical. So it can be used instead of this one if you like it. And I want your take your attention onto the graph on the right side. And you may remember that in the earlier part, I said the specific energy equal to y plus velocity square over 2g. And let's draw a graphic against a specific energy against y value. Okay, specific energy against y value. So you are going to write y values for different specific energies. And if you draw such a graph, okay, you will see that you are going to get a kind of graph like this. Okay, and this dashed line is exactly 45 degree. Okay, it is exactly 45 degree, and it goes in that way. So the specific energy values, when the specific energy, okay, and let's start a kind of smaller y value. When you keep increasing the y value, you will see that the specific energy will also decrease. Okay, increasing y value means that specific energy will decrease. You are going to lose some velocity. If you increase the velocity, I mean specific, if you increase the height of the water, then you are going to lose some energy from the velocity, and there will be a balance, and then specific energy is going to go less. And after a certain point, if you keep increasing the y value, you will see that the specific energy will also increase. Okay, this is a kind of quite a kind of usual graphic. I mean, this is this is a kind of usual graphic you can always experience in open channel flow. And in this graph, this part represents y value, and this part represent us the velocity head. And in total, you see that y plus velocity head, it means that pressure hydrostatic head plus velocity head, it means that specific energy. And specific energy makes such a kind of graph. And this point is called critical depth point. And any flow depth under this point represents as supercritical flow, because, for example, here the depth, if it is like here, the depth of the water flow is going to be less than critical flow. It means that your flow is in that type of channel is critical flow. So sorry, supercritical flow. And any depth higher than y critical on this graph is going to represent us that it is subcritical flow. Okay, and this graph on the middle, I mean the dashed line, that dashed line is specific energy is equal y line. I mean these two lines, this curve never match with this line. If it matches or if it crosses, it means that there is no flow. Okay, velocity is zero. See that when the velocity gets zero, then you are going to have a kind of specific energy is equal to y. So it's not going to happen never, but it will get closer and closer with the with like infinity. But it is, of course, in real life it's not possible. And then you are going to have a kind of hydraulic jump or something else. I will explain it later on today or next week. And at this point, when you experience y critical, please have a look at the equation here. If you replace, okay, if you replace this y critical value with this y value here, okay, in the specific energy, you are going to get that the specific energy at critical flow is equal to 1.5 critical depth. Okay, so please remember that this is important. At the critical depth or at the critical flow point, the total energy or specific energy of the system is equal to 1.5, 1.5 y critical, okay, critical depth. So this is our specific energy profile. And what you should learn and understand that, okay, let's assume that we have a kind of E value here, okay? We have a specific energy, given a specific energy value. Okay, let's say that a specific energy value is given for you at this point, like E, okay? And if any given specific energy value, and if you look at that graph, so go up and make a kind of drawing, just linear, just a kind of vertical line, and you are going to see that there are two possible conditions for that type of specific energy. For example, if specific energy given as 5 meters, for the 5 meter flow rate, 5 meter total specific energy, you can have a flow supercritical or subcritical. Both of them are possible. And if you remember, if you like to remember what I am saying, that please have a look at the graph which was given on Tuesday. Okay, here actually not the graph. I like to show you again the video. So you will see that there are two flows here. The first flow on the left side is subcritical flow, but the same amount of flow with the same conditions, but different velocities. But this is the same amount of flow actually, the same amount of flow. You are going to have a kind of supercritical flow on the right side. So it means that this system is, I mean, this experiment is showing us that it is possible to have two possible flows in any specific energy. It could be subcritical or supercritical. Okay, so this graph is also confirming us that it is possible for any given energy value, specific energy value, you can have either a subcritical flow or supercritical flow. How you can find it? That if the height or if the depth of flow is lower than critical depth, it is supercritical flow. If the depth of flow is larger than critical flow, then it is subcritical flow. It's quite an easy. So just remember that there will be always two solutions for any given problem in open channel. If it is that is given for you, and if I am going to ask you the alternate depth, then you are going to solve this by using this specific energy equation. Anyway, I am going to show you now one example. I think you are going to understand better. Okay, before going to the problem, I'd like to ask you again, is there any question you would like to ask? So I will solve that problem and the course will be over. I think solving the problem is not going to take too much than 10 minutes. So we have plenty of time to make any discussions if you need any clarification on this specific energy graph. Okay, guys, is it clear for you what is specific energy graph and what it tells us? Okay, it tells us that there are always two depths possible with any given specific energy for a flow. It could be either subcritical or supercritical. We don't know at the moment which one is going to happen, but any of them can happen because of the, I mean, preceding flow, okay, conditions. If there was a kind of, for example, a kind of obstacle or a kind of weir before the flow, most probably you have supercritical flow. But if it is just a flow before the weir, it is going to be subcritical flow. But most of the time in the problems, it will not given that what type of flow you have, and it's going to ask first you define that if it's subcritical or supercritical flow. Then after identifying it, it will be also asked you that what is the alternating depth for that type of flow. And you should calculate the alternative depth. Like if y1 is given, you are going to calculate y2 to find what it should be. Okay, if it is clear and if you don't have any question, I will solve one problem and I think you will get understand it better. And don't worry, next time I'm going to solve another problem. Maybe I cannot, okay, maybe I will not start hydraulic jump. Okay, guys, there is only one lecture left. And also Takmina and maybe most of you are also asking for some extra problems to solve and understand the topic well. So what I can do, maybe I will not introduce you hydraulic jump. This is going to be the last topic, okay? On Tuesday, I will solve you not only one problem, maybe a couple of more problems to help you to explain the topic in a better way. Then I think there will be no need to make any tutorial and there will be no extra topic. Actually, I was planning to introduce hydraulic jump before the exam, but maybe okay, it might be a good idea to exclude hydraulic jump from the topics of the midterm exam. What do you think that? Is it okay for you?
Yeah, good idea.
That's great. Thank you.
I think it is more reasonable. Okay, let's do not top up more topics. This is going to be the last topic for you, and I will solve one problem right now. And don't worry, on Tuesday there will be more problems, and I'm going to introduce and explain you more the topic with more problems. And okay, let's have a look at this problem. I think you will just remember that problem before because I solved it on Tuesday. This is exactly the same problem, but now I selected the same problem for you. And now I'd like to discuss that. And I added extra thing here, okay? And in the earlier part, you remember that the question was about define the type of flow, if it's subcritical or supercritical. Anyway, and in this problem, we just calculated the velocity as 3.333 meter per second. And also we calculated the critical depth. It is around 30 centimeters. And also we calculated the Froude number. You remember that it's also given like calculate like 275. These are done on Tuesday. And by looking at those results, we would easily say that the flow is supercritical. Okay, the flow is supercritical because the depth of the water is smaller than the critical depth, and even Froude number is larger than 1. Both of them are confirming that the flow is supercritical flow, right? Okay, now let's look at that. What question is asking us as a kind of addition? It asks us that, okay, if it is first identify if it's subcritical and supercritical. Now we know that it's supercritical flow, and now it is asking that determine the alternative flow depth if the character of the flow were to change. I mean, if this flow will experience a hydraulic jump and turns into this subcritical flow, like you have seen in this video. Let's go back again. Okay, I'm going to show you again, and take it a little bit. Okay, so at this stage we are talking about this part. Okay, at this stage we are talking about this part, and flow is supercritical, and after experiencing a hydraulic jump, the flow will turn into subcritical flow after the flow. Okay, subcritical flow after the flow, and if this water flow is going to experience a change in the state of its flow, so I want you to find the depth alternating depth of this flow. Okay, it's actually very easy. Let's calculate and see. First thing is you should know that what is the specific energy, and in this graph you will remember that there is one specific energy value for both alternative depths. Okay, so if you find the specific energy, it is the specific energy for alternative, depth 1 y2 and depth 2 y1, and here we are in this case. Okay, so we know what is y2 and we are looking for y1. It means that we are looking for the alternative depth of y1. It means that the depth should be higher than critical depth for the same specific energy value, and that's why we need to know that what is specific energy of the system, and specific energy is equal to y plus this, and you remember it's just given, and the depth is 0.15 plus this, and if you calculate specific energy by using this equation, it's quite simple that you will get the specific energy at 0.72 meters. Okay, 0.72 meters around. It is just a kind of approximately 72 centimeters. And again, you are going to solve the same equation by using this specific energy, but at this time we don't know what is y. Okay, and in this equation you are going to write what is QQ. We know the flow rate and we know the other values like the weight, but we don't know what is the depth of the water. And then you are going to get a kind of equation, a kind of cubic equation. Okay, and here, guys, this is a challenge. Some of the students are having difficulties to solve a cubic equation to find its alternating solutions. Okay, it might be challenging. I am pretty sure that the Nazarbayev University School of Engineering approved calculators are capable of making such calculations. But I am also pretty sure that you will still complain about it, some of you, and you will say that my calculator is not making such calculations. So in this case, you can use a kind of internet-based calculators. Let me show you, for example. Okay, and first thing is, okay, I will show you how you can use a kind of internet-based calculators. But let's look at this equation. So I will convert this equation a kind of cubic equation, and the constants are here 3, 1, 4, and we have minus 2, 25, and for y there is the constant is 0, and this is the overall constant in the given for the equation. So this is our equation, and I prefer to use a kind of website. This website is, I don't know if it is visible, the address. For example, calculators calculator soup.com is given a kind of online calculator for such case. And now I imported the constants for the constant of cubic parameter is, I wrote it here, and B is here minus 2.25, and this is 0 and 0. And when I hit calculate, it calculates for me the alternating solution root square. I mean alternating roots for the parameters what we are looking for. And let's go back, and I will share you again the so okay. Do you see my presentation slide now? The solution. Okay. So these are the alternative solutions. Look at that. There are 3 possible solutions because this is a cubic equation. And the first solution is minus. So minus is not valid because there is no depth like minus value. So you are going to ignore it. And the second one is equal to 0.15. You will see that this is exactly the same value, which is given 0.15. So this is the first alternative for this type of specific energy, for this amount of specific energy for given channel. And the alternative depth is 0.69 centimeters. So let's check it out. If 0.69 is larger than critical depth, yes, critical depth is around 0.29 centimeters. It is larger than this one. So I confirm that this value is a subcritical flow value, and this is the alternating value for this given energy, specific energy value. Okay, that's all, guys. Any questions? Okay, so my question is to learn what's specific energy in open channel flow. And this graph is important. I think you are now able to read what this graph is indicating, okay? And what is minimum specific energy, what is this critical point. I mean, if I ask you to draw such a kind of graph, a specific energy graph, I think you will be able to draw it, okay? So don't forget that this is going to be a kind of 45 degree, okay? So in this that it means that this dashed line is equal to specific energy equal y, and just this value also indicates that this critical depth, and over this value any depth is in subcritical flow, lower this any depth is supercritical flow. And also this graph is indicating that for any specific energy given, there are 2 alternative solutions. One is in supercritical flow, the other one is in subcritical flow. If you just understood everything as I told you, and as I summarized, I think you got the topic and you can solve any problem as it is given. And don't worry, I'm going to solve you a couple of more problems on Tuesday, and then I am going to close the session, and then you will be ready for the midterm. That's all.
May I ask?
Yes, please go on.
So in the last problem, could you please open the slide? Yes, here we have Froude number like 275. It's like more than 1. It means it's subcritical, right?
It's supercritical.
Oh, it's supercritical.
Yes. And who is talking? Takmina, are you?
No, it's Adana.
Adana, I mean, in the first lecture, I made a kind of typo and I corrected it. And this is correct. Okay, if Froude number is larger than 1, it's supercritical. Okay, please update your notes.
Okay, thank you.
Okay, there was a typo here. Actually, after the lecture, I listened my talk. I was excited talking the correct thing. The recordings. I just realized that I was talking the correct way. Even I was saying that when velocity is increased, the flow turns into from subcritical to supercritical. But somehow there was a typo here. This is the correct. I mean, if Froude number is larger than 1, it's supercritical. Okay. So here it is the case. Froude number is larger than 1, it's supercritical. And also the depth of water is smaller than the critical depth. It is also supercritical. Both of the values are confirming that the flow is supercritical. Any other questions, guys?
No. No.
Okay. If you don't have any question, I am going to close the session for today. Okay, guys, enjoy your weekend and see you on Tuesday. It is going to be the last day and last lecture before the midterm. Okay, so you will have a chance to ask more details, and if you have any questions in your mind about the midterm, I will be happy to answer them in that session. Okay, see you on next Tuesday.
Sorry, Professor, I have a question.
Malika, go on.
Can you please repeat about the specific energy? Why we need it? What does it show? Like it has units in meters, and why is it called energy? I didn't
Oh
get
yeah,
it.
I mean, this is typical, Malika, from fluid mechanics and hydraulics. I think you should remember that in fluid mechanics and hydraulics, we civil engineers, we always like to express the energy as a head, okay? I mean, like a kind of head, it means that always it is in height, it is in meters.
Okay.
The same, it's the same in Bernoulli. Do you remember that? Even Bernoulli is in like, okay, this is a called specific energy. Okay, look at this graph. I mean, look at this figure. Specific energy is equal to Y. Y is here hydrostatic hydrostatic head, and this parameter is V. I mean, velocity square over 2J is velocity head. Actually, components are heads, but this is called energy, specific energy. Of course, it is in the units of heads. It means it is in the units. I mean, civil engineers are doing it that way. If you are, for example, if you were in a different classroom in mechanical engineering department, most probably you were using the other units of energy, not meter. Okay, I mean, because look at this design, everything is meter, so we like to have the energy in meter too. It's more
Okay.
logical to calculate. Okay.
Yes, thank you.
Any other questions, please? No? Okay, guys. Thanks for coming today, and I'll see you on Tuesday. Bye-bye.
Thank you. Goodbye.
Goodbye.
Bye.
Bye-bye.